you for sharing this. Now we're coming to Dr. Yu Li from Tongji University. So Dr. Yu Li will present a report entitled From Force to Forms, Innovative Structural Design Based on Multi-Material Topology Optimization. And let's welcome Dr. Yu Li.
Thank you. Thanks for your introduction. Wait a minute. Can you see my screen now?
Yes, thank you.
Yes.
You can start.
Thank you. Thanks for the introduction and the invitation from IDD. Hello, everyone. I'm Yuni. I come from Tongji University. I have just finished my Ph.D. study and obtained my Ph.D. degree from College of Architecture and Urban Planning 2 months ago. Also, I have studied in the STEM team, which is the Center of Innovative Structures and Materials in MIT University. I have been supervised by Professor Mike Xie and Professor Philip Yuan during my PhD study. And during my PhD study, my research mainly focused on topology optimization and its application to architectural design. Especially, I have done some research about multi-material topology optimization. The title of my presentation today is From Forces to Forms, Innovative Structural Design Based on Multi-Material Topology Optimization. And this is also the name of my PhD thesis. Actually, the title was inspired by the famous book, Form and Forces, Designing Efficient Expressive Structures. I think maybe some of you have read this book. It's an interesting book which presents many famous and innovative structures. I like this book very much. Here are the contents of my presentation today. First, I will introduce some concepts about topology optimization and multi-material topology optimization. Then I will illustrate the architectural design workflow based on multi-material topology optimization. Next, I will show some practical and conceptual designs based on multi-material topology optimization. Actually, there will be 3 bridges to be introduced today. In the famous book, The 10 Books on Architecture, which Ruth Wells argued that every building should take into account firmness, commodity, and delight, which are regarded as the 3 essential principles of architectural design. Among them, firmness is considered as the most important principle. Structure-based architectural design, or called structural performance-based architectural design, which has been studied and practiced for a long time. Under this design concept, the architects use structural analysis techniques to assist the designing process and combine the form of buildings with the structural design. In this way, the buildings can have the structural efficiency and the elegant form at the same time. One or more reliable technical approaches is graphic aesthetics. Starting from Archimed's research on nerves, the development of graphic aesthetics gradually developed and matured until 19th century. Then some structural analysis or form-finding techniques emerged, like topology optimization and some other advanced techniques. Then I will illustrate some concepts of topology optimization based on ESO and BESO methods. The evolutionary structure optimization method, also known as the ESO method, was initially proposed by Emission and Steven in 1992. The principle of ESO method is very simple, which means gradually removing inefficient materials from a structure. Presented here is the topology optimization of a 2D truss subjected to a concentrated node using the ESO algorithm. After several steps of material removal, a two-bar truss is obtained. Based on the ESO method, Yimin and his team further developed this algorithm by introducing the bi-directional evolutionary structure optimization method, which is also called the BESO method. And in this method, both the material addition and removal can occur at the same time during each iteration of the topology optimization. And the example here, presented here, demonstrates the use of BESO method for topology optimization of a cantilever under a concentrated load. I think you might have seen these famous buildings designed by using topology optimization techniques. The Riverside Building in Japan, the Shanghai Himalaya Center, the Charter International Convention Center, the Bialic Pavilion by Zaha Architects, and some other conceptual designs. However, these projects are designed based on single material topology optimization, and the single material topology optimization techniques have limitations in applying to composite structures like steel concrete structures, but which are more common in building structure. The last part is an introduction on how to extend single material topology optimization to multi-material topology optimization. We were wondering that whether we can use two different materials to compose a structure in topology optimization process. The idea is very simple. One material suitable for tension is only tensioned, and another material suitable for compression is only compressed. The two materials will perform their best mechanical performance and forming an efficient composite structural system. As for whether a material is more suitable for tension or compression, it depends on the comparison of this material's behavior and tension and compression. For instance, for concrete, it's evident that it has excellent compressive performance, but weak tensile performance. Therefore, we generally consider that concrete is more suitable for compression. As for how to judge an element in the structure is tensioned or compressed, here we use the first invariant of stress tensors as a criteria, which is the value reflects the volume change of an element. When it's larger than 0, which means that the element is enlarged in volume, and this element is regarded as tensioned. And when it's smaller than 0, it means that the element is decreased in volume, and accordingly, it can be regarded as in compression. Then there are some other assumptions about the materials. First one is the two materials of the structures should be isotropic. The last one is the two materials should able for tension and compression respectively. And the third one is the interface between the two materials should have excellent adhesion. Based on this method, the multi-material topology optimization process is illustrated as the animation. After about 100 iterations, a reasonable multi-material distribution is achieved. The steel material is mainly located in the upper region of the continuum, responsible for tension, and the concrete is mainly distributed in the lower region of the structure, responsible for compression. The two materials form an efficient composite structure. So what are the advantages of multi-material topology optimization compared to single material topology optimization? Here, based on the same continuum, both single material and multi-material topology optimization are performed. In the single material topology optimization, the material needs to be both tensioned and compressed. In contrast, in the multi-material approach, two different materials, such as steel and concrete, are used for tension and compression, respectively. In this way, the multi-material approach can greatly reduce the amount of steel used. So, using the multi-material BESO method can generate efficient composite structures. Here we use this method to simulate a kind of bridge form, which is stress ribbon bridge. The structure obtained by using multi-material topology optimization is very similar to the two famous rail bridges, which are named Tongji Bridge and Colorado Bridge, designed by Qin Wu and Tong Yanlin, respectively. Similarly, this multi-material BESO algorithm is also applicable to 3D structures. Here, based on a 3D continuum, single material topology optimization and multi-material topology optimization are performed. It can be seen that in the single material solution, the structure is symmetrical, and the steel material is allocated in both tensioned and compressed areas. Where in the multi-material solution, the structure is not symmetrical up and down, where the steel material is only in tension. In this way, about 70% of steel can be saved compared to single material solution. Well, based on the proposed multi-material BESO method, which has been published on Composite Structures Journal, we have developed the architectural design workflow based on this method. The workflow mainly includes two parts: the topology optimization section and the control method. You know that structural efficiency is not only the goal that architects pursue. They need to consider other requirements like the functionality, aesthetics, and construction costs. So we can use the control methods like refining design domain or adjusting topology optimization parameters until the architectural requirements are satisfied. Okay, let's see some cases. The first project is a pedestrian bridge over a railway. This is a collaboration between our team and the T1 company. To across the railway, the Shenzhen government intended to build a pedestrian bridge. The conceptual design shows like this. Both the arched and the flat walkways are possible. There are three different forms of this bridge: the deck arch bridge with flat arch, the variable section PC girder bridge, and the variable dips spiral stepped PC girder bridge. Finally, we selected the last one. the variable dips spiral shift PC girder bridge as the conceptual form. Sorry. Here is the design process based on multi-material topology optimization from a 4-square design domain to a lateral design domain. We use the two materials, steel in red and concrete in blue, to build this bridge. You can see that by refining the design domain, we can get diverse designs. And by adding a non-design domain, we can drive the direction of the topology optimization. Here, we added a central vertical column as a non-design domain, and as a result, we obtained a different design with fewer branches. Moreover, by adjusting the filter radius, we can obtain a result with even fewer branches. Here is the structural analysis of this bridge. Here are the renderings of this bridge. The second bridge is called the innovative long-span steel concrete composite bridge. This is also a collaboration between our team, T1 Company, and the South China University of Technology. This work has been published on Engineering Structures Journal. Here is the background. CRF bridge, or called continuous rigid frame bridge, is a kind of common bridge type, but the stiffness of CRF bridge is hard to be satisfied when the bridge spans more than 300 meters. So we set a 3-span CRF bridge as the design domain and try to find a more efficient structural form. By refining the design domain step by step, we made the structure increasingly slender and more similar to a real CRF bridge. The pictures here show a CRF bridge named Tongji Jialin Real Bridge under construction and the view of its completion. You can see that the symmetry of the main piers is essential to the construction of a CRF bridge. So we must find ways to make the main piers symmetrical. By setting a symmetrical region with a reasonable width, we can obtain the bridge structure with symmetrical piers. After testing, we finally choose a symmetrical region with a width of 200 meters for the following steps. Additionally, we want to explore more forms with an expanded design domain over the bridge deck. As you can see, with different expansions, the results can be completely different. We choose the last one design domain for the following processes. By adding different non-design domains, we can also obtain diverse designs. Here we added the main arches and the vertical column as the non-design domains. Besides, we have also considered the multi-load cases, like the lateral seismic loads. Finally, we choose one competitive result and perform the post-design of the bridge. The steel components are designed as steel cables, and other parts are designed as concrete components, forming an efficient composite structure system. Here are the renderings of the conceptual design: the view from the boat, the bird's view, and the view above the bridge deck. Then we have applied a trial design based on the bridge. This is a diagram showing the main components, which mainly include main girder, main pier, and lower chord arch, column on the arch, and some other components. The static analysis shows that the new bridge is quite rigid, and the gross analysis of the mid-span deflection of the main girder also indicates that this composite bridge is competitive in terms of long-term deformation. In addition, we have also performed some dynamic analysis, and the results are consistent with the static analysis. For this completely new bridge form, we have developed a feasible construction method and the workflow. There is no need for special equipment or methods to build this bridge. It can be constructed completely using currently developed construction techniques. More importantly, compared with other bridge types, such as hybrid girder CRF bridge and cable-stayed bridge with similar spans, the proposed new bridge is also competitive in terms of economical indicators, which can save at least 17% of material cost. The last project is about a lightwork arch bridge. This is a bridge proposed to be built over Yangtze River, and this is also a collaboration between our team and the TUNE International Company. This work has also been published on Engineering Structures Journal. This arch bridge spans 470 meters. It's a half-through arch bridge with two main arches. We have done some form-finding work for the local structure of this bridge. Firstly, we have designed the window bracing by using topology optimization. Window bracing is the key structure connecting the two inclined main arches. We want the window bracing structurally efficient and lightweight at the same time. So we simplified the curved design surface into a flat 2D design domain and used the 2D structure. I used the 2D topology optimization to find the optimal topology with multi-node cases considered. The result shows like this. We call this new structural form variant K-shaped window bracing. By compared with other typical window bracings, including the K-shaped window bracing, the S-shaped window bracing, and the double cross-shaped window bracing, we can say that the new variant K-shaped window bracing is better in terms of stiffness and the stability. Besides, the new window bracing brings about a better visual effect with a lighter and more dedicated members and a more transparent appearance. From the aesthetic comparison between the proposed bridge with the new window bracing and the bridge with the conventional window bracing, you can see that the proposed bridge is more slender and elegant. Besides, we have also designed the spherical bearing by using topology optimization. The spherical bearing is also an important structure in this bridge. Based on the multi-material topology optimization, the tension and the compressed parts are identified. Finally, the spherical bearing is post-designed like this, which will be fabricated by metal casting. This is a rendering of the whole bridge, and this bridge is under construction now. To conclude my presentation, there are three small points to consider. The first one is based on multi-material topology optimization. It's possible to achieve efficient, aesthetically pleasing, and economically cost-effective structures in the conceptual design phase of buildings. The second one is by using multi-material topology optimization, it's possible to find innovative structural forms that are even more competitive than those designed by experienced engineers. The last one is the application of multi-material topology optimization in both practical and conceptual projects demonstrates its significant advantages in structured performance-based architectural design. Thank you all for your listening and attention. Any questions you may have are welcome.
Thank you, Dr. Yu Li, for your amazing presentation and very solid knowledge. And now I know more about how to design the window bracing. And yeah, and if you have more questions, please feel free to type in the chat or directly open your mic.
I have a question. Thank you, Dr. Li, and I think your presentation showed a lot of your work in your PhD student, in your PhD stage, and I have a question that is about the structural performance laws. Because I remember you mentioned a lot of about you applied design domain. You changed the design domain and the applied non-design domain. In your page 19 and page 29, page 30, have you compared the performance, the compliance between the original topology optimization and your and the new design after changing design domain and non-design domain?
Thank you, Albert. Thanks for your question. Sure. We have used many methods like refining the domain and changing the parameters to obtain diverse designs. The purpose is that you know that in the design process, architects usually want to have the structures that not only satisfy the structural efficiency, but also need to consider other aspects like functionality and cost something. So we need to control the fellow topology to satisfy these requirements. So we use many methods to obtain diverse design. Actually, you mentioned that the new results usually have lower structural efficiency compared to the optimal structure, which is not effective, not influenced by this method. Yes, you are right. Actually, these researches and these studies have been performed by many researchers. There are many researchers like our members in the CISM team have done these researches. So I don't think this is the main focus of my study. So I just set their researches, but don't research these aspects in details.
Okay, thank you for your answer.
Thank you.